Hello interwebs, welcome to Let's Fix Computers. I've got a Dell here. This is an Inspiron 17 5000 series. And sorry, I'm just leaning across to plug in this charger again. And it doesn't turn on. Alright, noises of strain. Okay, so it's the old story of the charger light goes out. So I've got the charger here. As you can see, the light on the charger tip is on. However, if I plug it into the laptop, the light on the charger goes out, and the light on the charger stays out until I power cycle the charger. So I've now got to unplug the charger and plug it back in again to reset the cutoff. So now I've got to unplug it for a bit longer than that. So this is caused by a short circuit somewhere in the laptop. Let's open this up and take a look and find out if we're lucky and it's just a bad capacitor somewhere, or if we're unlucky and it's a dead VRM that has put 19 volts from the charger into the CPU. So let's roll the graphics. Whoop. God, that does not want to come out, that guy. Ooh. Just a clip that's holding on. I'll try going somewhere else. Oh, there we go. Right, we're in. So our DC jack is coming in, and annoyingly, the DC jack connects under the motherboard. So we might have to go. Straight in with motherboard removal. I'm just peering at the motherboard just to see if I can see anything screamingly obvious. Let's turn on the multimeter into resistance mode, and we'll just do some quick stabbing and just check if we are probably dead in the water. If we're shorted through a CPU VRM, I'm probably going to give up. Alright, so I will check. So this area here, let me punch down a little bit further. So this area here, this is CPU VRM because our CPU is there. This is going to be our GPU because it's got VRAM around it. And so this area is all CPU VRM because these are big powers. This is all power management because you've got big inductors and fat rails and big capacitors and stuff like that. Likewise, if we move across here, that's our GPU VRM because, again, that's all big power stages that are going into the GPU. Although those are MOSFETs, whereas these guys are actual power stages. You can tell because these guys are 8-pin packages, whereas these are multi-pin packages, and there's no high side and low side. It's all built in. So yeah. So this side where the inductors are, that is our output into the CPU, which means the input is on this side. And so this big capacitor here, that is going to be on the main power rail feeding into these power stages. So if I check our resistance to ground there, let's see what we see. And we've got 0.5 ohm. That's good. Do we know what CPU this is? Just going to open it up a sec. Hold on. Right. I think this is 7th gen or older. Oh no, it's even older than that because this is DDR3. So yeah, this is probably 6th gen, maybe 7th gen, but I doubt it's 7th. So I would expect a CPU of that vintage to be giving sort of 3.5 ohms, which we can test for actually. So hang on a sec. We can answer this question very easily. I'll put my black probe on a screw hole again. And if we check the output to one of these inductors, there we go. We've got 8 ohms there. So we definitely know we're not shorted through a CPU VRM because we have a different resistance on the output of the VRMs to the input of the VRMs. So these are forming a wall. They're a barrier between the main power rail and the CPU. If we were seeing the same resistance on either side, it means one or both of these would probably have failed and was shorted through, which would be catastrophic. Let's do the same test over on our GPU. Now, GPUs can have super, super low resistance to ground. So, again, might not be so lucky. So, I'll check. Let me see. I think this is input side and I think this is output side because the inductors have to be on the output. So I think we're going this direction and then back into the GPU. So let's just check that one of those inductors. 40 ohms. Okay, that's a lot higher than I would expect it to be. Well, if you say so. And we'll check the input side. So, looking at the input side, we've got capacitors across these middles. Two of these will be the high sides, and two of them will be the low sides. The high sides connect to the main power rail. The low sides connect down to ground. So the easiest way to check is, well, we need to figure out which side is ground. So I'll put my black probe on a screw hole, which is true ground, and one side we should find is probably slightly higher than the other. Right, so that's about half an ohm, 0.4. Let's try the inside edge now. That's giving like 1 or 0.1 or 0.2 ohms. So the inside edge, that's absolute ground. So the inside, those are our low sides, and the outer ones are the high sides. And again, so on the input to the high sides, we're seeing about half an ohm of resistance. And on the output, we're seeing that 40 ohms of resistance. Let me just try and bring that up again. So let's just grab the output of those ones. So yeah, 40 ohms is very high. But the point is that's not shorted. So we don't really care if that's out of the ordinary. What we care about is that it's not the same as the short circuit we're seeing on the main power rail. So this looks good. It looks like we're onto something here. Oh. I see. Well, there's your problem. How did I not see that? I was just so laser focused on VRMs that I didn't see that there was a bloody great crater in the board. This is why you do visual inspections. This is what the visual inspection is for, because you might have a crater in the board. Okay, right. Let's take a closer look at that, shall we? One moment while I get the microscope set up. Okay, so what exactly are we looking at here? We've got two power supplies next to each other that are almost identical, and they have the same controller chip on, and one of them's slightly bigger than the other. So this is going to be our 5 volt and 3.3 volt power rails. So kind of important, you need these to run. The larger one with the slightly bigger inductor on the right here, that's probably going to be the 5 volt rail. So my guess is that this is the 3.3 volt power rail that's gone nuclear. So that's gone pretty spectacularly as well. If I just tilt the board up so we can take a closer look there, you can see that this thing has properly gone out with a bang. So I don't think there was a capacitor there because those pads are round pillows, so that was no stuffed. And same thing there, those are round pillows, so that was probably no stuff. And if we look over here, this one has got the capacitor there, but there's nothing else next to it. So it looks like, apart from maybe that, that's probably a capacitor under there. Apart from that capacitor, there's nothing here to have actually exploded. Just the controller itself has just spewed its guts out. So we've got a twofold issue here. Is Can we replace that? Because obviously that's got to be replaced. And also, have we damaged anything downstream? So this may have spontaneously combusted, or it may have been overloaded by a short circuit downstream. So we might still be dead in the water here. The first thing we should do is take this guy off the board and see if the rail itself is still shorted. If we remove this and find that the output is shorted, there's a short downstream, and that's probably bad news. But if we remove that and all of the short circuits disappear, probably means we just need a new 3-volt regulator. So I'm going to take the motherboard out of the laptop and we'll take a closer look and see if this is actually salvageable or not. Yeah, there's a skid mark on the other side as well where it's just completely overloaded the via. Well, let's take bits off and see what's left. So on the other side of the board, you can see where the other side of that area has massively overheated as well, and left a big old skid mark on this side. There's not a lot going on over here, though. This inductor is not populated. We've got a bypass cap there, but other than that, I don't think there's anything going on this side. So as long as the board hasn't got shorted inner layers, we might be okay there. You know, we'll probably survive without that capacitor, or we can just double stack the bypass cap that's on the other side of the board. So, not super panicked about that. I'm just going to have a quick poke at this and just... Is this just coming off of the board, or what's the deal? No, it's still stuck down. Just crispy. Alright. That anything, or is that just soot? Yeah, that's just soot and skid marks. Alright. So, I'll get the hot air on this, and we're going to start heating up that. We're going to start heating that up and just see if it'll come off. It's probably welded itself to the board, so this thing's probably going to put up a fight, and I'm not looking forward to this. But, yeah, let's see how we go. I'll put some flux all over this, although I don't think flux is going to help us right now. At least try and protect the areas. Smells crispy. Okay. Right. The pins on the left side have welded onto the board. So I've just left the chip tombstoned there. So now it's just flapping in the breeze, and I can just get in there and maybe just cut it away without ripping all of the traces out. But yeah, this don't look good. This is going to require surgery, and I am not a surgeon. That's a very good view. All right, let's have a... Oh, boy. Oh. Oh, what happened to you, dude? What happened? There we go. All the pins are gone. Alright, let's get you out of the way. This will be a generic chip. The 5-volt rail chip will be identical, and the voltage is probably set by a resistor somewhere nearby. Okay, right. Let's get some alcohol and the toothbrush on that and just see what's left. Okay, so with just the regulator removed, let's fire up the multimeter and let's just see what we've got. We might have more shorted components there, like this this capacitor might be cactus as well. But let's just see if anything has changed. So, back probe on a screw hole, and I'm just going to check. Firstly, I'm going to check our main power rail again. Our main power rail is still shorted. And And that's probably because like these layers are probably shorted together. We're probably going to have to dig out this short circuit. So to find, well, let's just check this output anyway. All right, we've got 2.5 ohms over there. I'm going to see if I can get a schematic for this board so we can find out what the pin out of this chip is. It's an AAL15, right, LADO71P. LADO71P. It's under the heat pipe. So I've got here the schematic for the LADO71P. It's a Skylake U board with an AMD GPU on it. And if we have a look at the board itself, you can see that the inductor right next door is PL100. So if we search the schematic for PL100, that brings us down to this page here. And as you can see, we've got two identical voltage regulators for 3.3 volts and 5 volts respectively down in the bottom right. And PL100, that's that guy there. So that, as predicted, is our 3 volt rail. So if we move back along here, this is our exploded chip. So let's take a look at the pins on this guy and see what pins we're missing and what we're up against here. So let's start from pin 1 here. So pin 1 is labeled BS, and it goes back around through PR100 and a capacitor and back down to the output. So pin 1 is kind of gone, really. It was there, but it was holding on by a thread and just flakes off. Okay, so we're going through this capacitor and we're coming back through to here. So that is our line coming into the output, and that bit is bridged across there. So it looks like PR100 is just no stuff, and that is PC102. So let's just quickly check if PC102 is shorted or not. So let's... it doesn't connect to ground, so it's not going to be shorted to ground, but we can just check if it seems to charge up. Yeah, so that's high resistance or out of range. You know what? I could just go into capacitance mode and just see if we're actually getting a reading from that. So because this isn't connected at the other end, we can actually measure this in circuit. Yeah, 100 nanofarads. So PC102 is fine. This is no stuff, and we can connect this back to a replacement chip with a jumper wire. So pin 1, no problem at all. So what's next? So next up, we've got pins 2, 3, 4, and 5, and these are all inputs. So this is all power in from the main power rail. So, spoilers, I've said all of this already, but I forgot to unpause the recording. So you can see here we've got PJP105 or PL102. Now, if you remember back, PL102 was on the back of the board and it was not populated. So that being the case, we care about PJP105. So this is a jumper that allows us to disconnect. So what I then did, there's PJP105, and I just removed the solder blob that was across that jumper. So this is now disconnected the input from the main power rail. And so now, if I put my black probe on ground and we probe the input side, so this is the main power rail, we're now seeing high resistance on the main power rail. So we've resolved the main rail short by just disconnected it from the fault site. And if we measure this side, you can see that we've still got, there's our half ohm short to ground. So there's a half ohm short to ground probably buried in here. So with that disconnected, are we still shorted on our output side? So if we measure the output pins here, there's that weird 2.5 ohms. So I don't know if that's a problem quite yet, but you know, let's just look at the other pins first. So that's pins 2 through 5. The next one up is pin 6, which is labeled LX. And so pin 6 is this guy here. So let's just see if that is shorted We don't know what it's supposed to read. I'm not quite sure what LX 3 volts is, but let's see if it's got the same half ohm short on it. And no, that's also reading 2.5 ohms. So that doesn't have the short to ground. So that is already pretty well isolated. In an ideal world, we kind of want to just dig out around it a little bit more, because if we press down on that pin, it might make contact with an inner layer and short out again. I wonder if we can see... Oh, LX 3 volts. That's the same as the output. This is just this looks like another output or feedback. Oh, it's right in front of me. LX 3 volts, that's just the output. That's odd. Just pin 6 is also an output. Okay, fine. So, in that case, looking on the board again, so this guy connects across to here. There's probably, those vias will probably bridge across on the other side of the board to there. So, as long as this guy isn't contacting this inner layer, that's okay, and that's reading correctly. So, let's move up. Next up, we've got pins 7 and 8, which are ground. And if we check those on the board, you can see we've got 7 and 8, and those connect to the ground pad in the middle. They connect to this pad over here, and they connect to this big ground pad here. And those are all intact. And everything else around the other side of the chip is also in good condition. So on the schematic, we've got our 2 ground connections there and there. And likewise, we've got another ground connection here. And everything on this side of the board, all of the important stuff for feedback and enable pins and stuff like that, is all good. So really, our input pins, those are the ones that got messed up. So there's a good chance that this can actually be repaired. So my main concern now is that the output is at 2.5 ohms, and I don't know if it should be or not. So I'm going to find out. I'm going to get some opinions on that to find out whether I should bother continuing. While we're here as well, we should probably just check the 5-volt rail and just see if there's anything interesting going on there. So we know that the input to it is fine because it's not shorted, but what's the output reading? All right, the output is high resistance. So we're up in the tens of kilo ohms there. So the 5-volt rail looks like it's completely fine, which is a good sign. Just taking another look on the back of the board. So looking on the back of the board, so PL102, that connects back to the main power rail, which is here. Then we've got a resistor, we've got a capacitor here. I'm just going to check. I'm going to check if that capacitor reads short, which probably will. You know what? I wonder if this capacitor went short circuit and we just melted out. We just melted out the vias. I'm going to quickly remove that capacitor and just see if the short circuit disappears or not. I'm going to take a pot shot at that. You can see that little connection bridge across there for the LX 3 volt pin 6 as well. That capacitor is short circuit. So 12 ohms. Right, so 12 ohms to ground. That's a partial short, and that's just because of inner layers. There's still heat in the board. That might resolve itself when the board cools down. However, I think we found our root cause. So our root cause was this bypass cap. It's always a hecking capacitor. This bypass cap on the back of the board went short circuit and pulled the main power rail to ground through these vias and just blew up, just completely exploded the vias. So I'm going to find out if that 2.5 ohms is something to be worried about on the 3.3 volt rail. Otherwise, it looks like we found our cause. It looks like we might have an exit to this. This might be a fix. Okay, so I've conversed with Greybeards, and I'm told that 2.5 ohms on the 3.3 volt rail is almost certainly going to be a dead PCH, which is game over. If the 1 volt rail had also been shorted, that would have been evidence, but our 1 volt rail going into the PCH is not shorted. But given that we've cleared the short on the main power rail, we can just inject 3 volts into the 3 volt power rail and see if the PCH heats up. And that will also give us our answer. And I'm just going to do that for the sake of it, because there's a couple of people who've got their money on that one. So let's just let's light it up and just see if we can evidence that. And that probably is going to be us done. So bit of a shame for this one, but it will be good to show anyway, just because if we show what failure modes look like, it helps people identify them themselves. So if you encounter something that's exploded like this, you can find out whether you should even be bothering to look at it, basically. Because, yeah, if the PCH is dead, we're not changing the CPU. That's not a thing that's going to happen. So, let's just clean it off for funsies. So for setup, I'll just dial 3 volts into my power supply. And this seems like as good a time as any to test a different method of doing the thermal camera. I'm going to try connecting the thermal camera just directly to the PC, which is actually possible with the InfraRay P2 Pro that I use. You just don't get the InfraRay software. So it's going to be a black and white image and probably isn't going to look very good, but we'll just try it out just to see if it's viable as thermal camera use with direct capture. So let me just try sticking my thermal camera onto the bench cam. Oh, there we go. That's not too shabby. There's my hands. So I'm going to try just poking this thing. So power supply is on, and I'm just going to hold that against the jumper output, and we're probably going to see the PCH light up there. Here goes nothing. There we go. So that's just gone straight up to my current limit of 2 amps. And yeah, the PCH has lit up like a Christmas tree. So that's a shorted PCH, which means we lose. So yeah. However, this thermal camera mount is not bad. I might put a little bit more effort into this and see if I can't make that more workable. It's a lot easier than capturing it by looking down through the camera app. So, just a thought. All right. So that's where we leave it for today. So it would have been fun. I would have been quite interested in trying to. I would have been quite interested in trying to see if I could fix up that damage and put a new regulator on there, because that looks fairly. Because the regulator damage looks fairly fixable, but that's all completely in vain with a dead PCH. So that's it. So that's where I'm going to finish up today. Thank you to all of my subscribers and supporters. I hope you guys found that interesting as a failure mode. The fails may not be as exciting because you don't get that rush of success, but sometimes you learn more from the fails, especially like now where we can see concisely what happened. That capacitor, that capacitor was almost certainly collateral damage, not the cause of the failure. So yeah, because the regulator had gone explode, the PCH died, nuked the regulator, and the regulator exploding killed the capacitor. So that capacitor was nothing to do with it. So thank you for tuning in, everyone. I'll see you again. Bye.